Here on the slide, you can see the list of some very simple panel estimators. And when I say they're simple, it means that there are more complicated estimators, which we will quickly discuss in the part devoted to co-integration analysis. But for now, let's focus on the simple ones. So there is a pooled Oilless estimator. There is also fixed effects estimator, which comes in two forms, one-way fixed effects and two-way fixed effects estimator. There is also fixed effects within group estimator and the random effects estimator. Let's go through these estimators one by one. And let's start with pooled Oilless estimator. So on this slide, you can see some general equation for panel regression model where y is a function of x1, x2, and all the way to xk. If we would like to calculate the number of observations in this model, we take I, which is the number of cross-sectional units, like the number of countries, and we multiply it by t, the number of time periods, let's say like the number of years. And this is how we get the number of observations. And for this model, the number of parameters is equal to the sum of all betas, there are k betas, plus the intercept plus 1, so k plus 1, this is the number of parameters. From this equation, you can also get that the intercept together with the slope coefficients, they are homogeneous. In a sense, they are the same across cross-sectional units and time periods. And this is actually the main limitation of the pooled Oilless estimator, because this estimator does not distinguish between the various cross-sectional units like various countries, and it doesn't tell us whether the response of y to axis over time is the same for all the cross-sectional units. So this is actually the summary of what I've just said, that we have the homogeneous intercept and we also have homogeneous slope coefficients. So the response of y to the change in axis is the same, it's equal to beta 1 for all the cross-sectional units, and the intercept is also the same for the countries for cross-sectional units. And because of this, very often this estimator is known to suffer from the problem of heterogeneity bias. And so heterogeneity bias is when we pool the estimates by assuming that they are all the same across countries, across cross-sectional units, which is often not the case because countries are extremely diverse, people are extremely diverse, and it's a very big mistake to assume that countries and people and cities are homogeneous. And when we impose this assumption incorrectly, the estimates are biased and inconsistent. So therefore, this is not really recommended to use this estimator, and it is always better to use some other type of estimator, like for example, fixed effects estimator. So let's start with its first type, one-way fixed effects estimator. So one-way fixed effects, this is the fixed effects model where intercepts are allowed to differ across cross-sectional units, countries, people, etc. So we say that this model has individual effects. And if you look at this equation and compare it with the previous one, you will see that now the intercept comes with the subscript I, meaning that it is different for each country, for each cross-sectional unit. So the number of observations is calculated in the same way. This is just the product of the number of cross-sectional units and time periods. And if we would like to calculate the number of parameters, so first we sum all the betas, there are k of them, plus I, which stands for the number of intercepts. So once again, in this model, the intercept is different for each cross-sectional unit, and this is how we introduce individual effects into the model. And when the intercepts are different across countries, then we say that this is a fixed effects one-way estimator. So that was just the theoretical equation, but now the practical issue is how to estimate this model. And actually we can do this using the concept we're already familiar with, the dummy variable technique. So we assign the dummy variable for each intercept with the exception of the first one. And don't forget that we do this in order to avoid the so-called dummy variable trap. So now alpha 1, this is the intercept, and here we've got the sum sign where alpha j multiplied by dji. So alpha j, this is the individual intercept, and d, this is the dummy variable. For example, d2i is equal to 1 for cross-section number 2 and 0 otherwise, D3 is equal to 1 for cross-section 3 and 0 otherwise, etc. And the rest is the same. So if you would like to estimate a one-way fixed effects model, then this is the way to do this. So please assign the dummy variable for each intercept with the exception of the first one, and we avoid adding the dummy variable for the first intercept so that we don't fall into the dummy variable trap.